this is going to be like an ad hoc derivation of the continuous uniform probability distribution density function, as well as its corresponding mean and variance formulas. Now, sorry, just got a bit tired doing the binomial probability distribution mean video. Okay, anyhow, what's key about this is the probability density function is represented by this particular picture here for your domain of real numbers, where it's essentially the probability density function is defined as the following way. P of x equals, and I need to put in a case value here, so it is 1 over b minus a, 1 minus over b minus a for a is less than or equal to x is less than or equal to b, and 0 everywhere else. The 0 everywhere else and the 1 over b minus a needs to be there in order for the axioms of probability to be satisfied. Namely that if you add up all the probabilities of disjoint events, they sum up to 1. And for some, since we're dealing with real numbers, which are continuous quantities, we can do them using an integral, and therefore take the integral of a function. For a uniform probability distribution function, as seen here by this constant horizontal line, the probability function is going to be a constant. So we're allowed to set this p of x equals to c, and then from a to b, the integral must capture 100% of the probability. So we have 1 equals integral from a to b of c of dx. Now by the second fundamental theorem of calculus, I can break this up into, or by taking its antiderivative, I get cx. Then by the second fundamental theorem of calculus, I can plug in the endpoints b and a and subtract them from each other. cb minus ca, but I can factor out a c out from that very easily. Yeah, actually, let me just do that. cb minus ca, I can factor out a c from this to get c times b minus a. And then I can solve for the constant c just by dividing both sides by b minus a, and boom, I get p of x equals b minus a. And I already mentioned why this is necessary. Okay, now let us derive the mean and variance formulas of the uniform continuous probability distribution. So mean is an expectation value, so I just take the integral of x times p of x from endpoints a to b. So this is going to give me 1 over b minus a times x, but that's really nice all I'm doing because that's just a linear term. So all I have to do is turn this into a quadratic, and then, yeah, it's raised to the power of 2, so I bring like a 1/2 to the bottom as well. So then this just becomes 1 over b minus a 2 times that, x squared, and then I need to go and square the entire environment here, and then a to b. Now if I do this here, I'll get 1/2 over 1 minus b over a, 1 minus b over a, b squared minus 1/2 1 over b minus a squared. All set down, but we can do some nice, even simpler algebraic simplification, because b squared minus a squared here, as seen here, once we factor out 1/2 1 over b minus a, and we get a b squared minus a squared. This is just factoring. B squared minus a squared is just a difference of 2 squares, so I can express this as 1/2 of 1 over b minus a times b plus a, b minus a. And the b minus a in the top and the bottom cancel out, so I'm just left with 1/2. Whoops. 1/2 b plus a. And we're done with that. That's the expectation value, or the average. Okay, now the variance. The variance is basically the distance of the expectation value from a constant mean squared or basically this thing here, x minus mu e of x minus mu squared oh wait, sorry, my god, this is driving me crazy. So minus mu squared here, and I've done this derivation dozen of times to death, but essentially if you go and expand in the inside, you would get e of x squared minus 2 mu x plus mu squared. And because probability distributions are functionals and hence linear transformations, I'm allowed to do the following things. I can split up the expectation values into each of these individual free terms by themselves, so I get e of x squared minus e of 2 mu x squared minus e of 2 mu x plus e of mu squared. But I can factor out any constants outside of here, and an expectation value of a constant is just the constant in and of itself. So I just get e of... Wait, something smells fishy here. Let me just take a look. X squared minus 2 mu x squared. Oh, okay. Just give me a second. E of x squared minus 2 mu e of x plus e of mu squared. Okay, so that just comes with linearity properties. Because it's a constant, I can just end up with e of x squared minus 2 mu e of x plus mu squared. Also, e of x just simply equals mu itself, so I just get e of x squared minus 2 mu squared plus mu squared. So then this becomes e of x squared minus mu squared. And this quantity here is called the second moment of probability when dealing with, not moments of inertia, but raw probability moments is what I would say. Yeah, moments in probability. And the variance is the second moment of probability. The expectation value, or the average, is the first moment in probability. And then skew and kurtosis being the third and fourth, we're going to deal with that later. But yeah, we're going to use this formula here. So essentially we need to go and, going back to the continuous uniform probability density function. So variance of x would be just the integral from a to b x squared f of x dx minus the mu squared, which is essentially the e of x that we already found over here. So then this is just e of x squared. Now recall. Pardon me. Yeah, we're doing the sum of the entire thing. So yeah, this should be for the entire thing. So let me make sure that I bracket everything here. Actually, yeah, so I do it for the... No, the dx is just for here. Yeah, the mu squared is constant. I leave that alone. I leave that alone by itself. So let me put it like this, yeah. And then we're done. Now recall that we got that mu equals 1/2 b plus a. So we can plug in that directly into here. That'll give us an answer for that. But for now, let us go and do the variance for this. A to b. So that's x squared, probability density function, times 1 over b minus a dx. So minus this quantity all squared now I get x squared over b minus a dx minus this crap. But now I get like a cube out of this, so then this becomes pardon. X cubed over 3 times b minus a. And I need to square bracket this again. AB like that minus this quantity here. All right, and now we do the difference of cubes for this thing. So then it's, yeah, b cubed. Sorry, b cubed minus a cubed over 3 times b minus a. Come on, cooperate with me. So then this becomes minus a quarter of b plus a squared and then I need to look up quickly the sum of cubes. Okay, I got the sum of cubes formula. Sorry, not the sum, the difference of two cubes formula now. So this will be b minus a times b squared plus ab plus a squared. Is it a 2ab or is there an a over there as well? Let me go in. But yeah, this will be divided by 3b minus a. This is minus a quarter b plus a squared. Nope, it's a single term, so plus ab here. Well, it cancels out to this. B squared plus ab plus a squared over 3 minus a quarter b plus a squared. Okay, and in order to put these into put these terms together, we've got to put them into a common denominator. So we have a 3 and a 4 here, so the least common denominator of both will be 12. So this I'm going to multiply by 4 over 4 times this stuff that we have left here. Minus 3 over 3, 1 quarter, b plus a squared. So then this is 1 over 12, 4b squared plus 4ab plus 4a squared. And then minus 3 of b plus a quantity squared. That's going to be 1 over 12. Let's see, let's expand this out. 4b squared plus 4ab plus 4a squared. That's minus 3, and then b squared plus 2ab plus a squared. Okay, that's good. 1 over 12, 4b squared minus 3b squared plus 4ab minus 2 minus 6ab, pardon. B squared minus 3b squared minus 6ab, gotta be careful of the negative sign here. And then minus 3a squared. And I'm missing a term here as well. Oh yeah, 4ab minus 6ab and then plus 4a squared. Plus 4a squared minus 3a squared. Yeah, that's after I permuted all the terms around or moved all the terms around together. So from this, we get, okay, 1 over 12b squared minus 2ab plus a squared. So that is simply b minus a squared over 12. Yep, and that is indeed the variance formula of a continuous uniform probability distribution. Yep. So to summarize as a result, for this thing here, we end up getting that e of x equals 1 over b plus a. What was it? What was it? I forgot what I derived. 1/2 b plus a. And variance of x equals b minus a squared over 12. And that is it. Thank you. Hope you enjoyed this video. Soon I'll go and show how this works for a discrete uniform probability distribution as well. Be careful, for discrete, the domain will be natural numbers, not real numbers, as is seen in this case. Okay, see you until the next one.